Hey, what's going on, everybody? So for the second part of this three-part or so series, I'm going to discuss the results and discussion of the PhD thesis related to complexity-based convolution neural network for a metamorphic malware detection. So in the previous set of slides, one thing we looked at was the PowerPoint presentation, providing introductory to the topic. Now, before we go into results and discussion, I want to quickly mention something related to the benchmark data sets that isn't fully fleshed out in the PowerPoint slides, and that's related to these graph benchmark data sets. So in the full thesis work, we looked at 3 groups of data sets which correspond to 3 different types of graph behavior, one being the core, sightseer, and Facebook page data set. And table 3.3 here has a summary of all 3. Ultimately, one of the things we want to do is before we demonstrate that our models are capable, we want to show that the models on their own work well for benchmark data sets that have a known particular behavior and that are well established in the literature. The first being the core data set consists of over 2,700 scientific publications and is one of 7 classes. So that makes it a multi-classification task corresponding to a category in the scientific literature. So just imagine you have all these scientific papers and you want to see if this is science or biology. So in this work, node features are binary, presence of a word or not, which is a bag of words. We discussed that. Vector size of 1,433. So that's the size of the corpus. And then each citation between each paper is encoded as one of 5,429 directional edges. So in this work, the nodes are individual papers and the edges correspond to whether one paper cited the other. And that's hence why it's directional, because it only goes one way. One paper cites one other. And again, the feature is just a bag of words, whether or not a particular word was used. So ideally, you'd expect some words that has the word compound, atom, right? Benzene, whatever it may be, to correspond to a more chemistry-focused paper, and some other words to correspond to a different type of paper of one of 7 classes. The sightseer data set consists of 3,300 plus scientific publications, one of 6 classes, so multi-categorical classification. And here we have 4,700 directional edges, and each node includes a 0 to 1 valued word and can absence presence of the corresponding word from a dictionary. Very similar to the core data set. The Facebook page data set is a little different. We have much larger size in terms of the size of nodes, over 22,000, each representing verified pages on Facebook. Now we have 340,000 edges, each identify a mutual like between 2 pages. And node features are extracted from the site descriptions that the page owner creates to summarize the purpose. In total, there are 128 node features, and each page is classified in 4 classes. So we have fewer classes. Here we have the 4 different types. And there's only 128 node features. So compare that to these other ones that are encoding the particular words. 1,400, 4,007, that's 1,400, 3 edges, 3,700. This one has 128. So the size of the feature vector of each node is much smaller, but there's many more edges. So consider that when we're testing and the difference between each model. So here's the different nodes. Again, low feature size for the Facebook, high node count. Number of edges is much larger. Class is all multi-categorical. Training and validation split is just used for the purposes of when we're actually validating how many samples we get gathering for this. A few things before we go forward is model performance metrics. There's a few different ways that we can test the validation performance of a model as we're learning it. One being the loss. Ultimately, it comes down to cross-entropy loss. We have a generalized form. Cross-entropy is a generalized form of the binary cross-entropy, because at least for this work, we have to use this because now rather than just doing malware versus benignware, now we, for these other benchmark data sets, it can the training example or validation example can belong to one of 5, 7, or 8 different training classes. So we need to be able to encode that loss in the form of cross-entropy. That kind of makes sense for us. There's a little comment here, but it's not too important for k-fold cross-validation. Accuracy is something that is to be considered. Macro average just takes into account the class imbalance. So we determine the accuracy for different classes, but we account for the number of training examples. That way we're not concerned about class imbalance. And additionally, F-score being a harmonic mean of precision and recall just takes into account true positives, and false negatives. And that's just sort of a general representation of F1 score. So with that, we'll just go right into the slides. Turn my pointer on. That. So this was the last slide that we covered, where we talked about generalization and how we want to execute these malwares in sort of a virtual machine snapshot. And we're executing malware in the presence of benign-ware, and there's a certain probability associated with that. So right to the benchmarks. So there's a lot here, but all I really want you to take out of it is that at the very top here, A, we have the validation loss, macro accuracy, F1 score. So those 3 metrics for the core data set, the Sightseer, and the Facebook. So that just summarizes it right there. One thing to have note, maybe it's worth mentioning also that the red and blue plots correspond to two different models. The vanilla model is the red ones. That just corresponds to a simple graph neural network with attention. And the blue plots correspond to a fractal dimension model, which is the radius of gyration fractal dimension. So this more speaks to the previous work and when I was talking about the different types of complexity analysis and then the graphs, and as they get farther apart, we're encoding that information. This is actually the blue right here is when we actually use the complexity layer to feed back into the model. So I think I actually have it a few slides back. It's pretty much just summarizing perhaps pretty much the slide. So this is the radius of gyration or complexity layer that's included, and we're capturing the complexity and feeding it back into the model. So I did explain that in the previous video. So that's what this fractal dimension model. So ultimately, if we're looking at loss as an example, which we see the loss for all 3, one thing we're looking at is lower loss and lower standard deviation. And that just means that and this is ran over, I think 18 iterations. So we're initializing the model 18 different times. And then we're tracking the loss as a function of training epoch. And these are all validation sets, just so you know, right? So we're not looking at the training, which is typically prone to overfitting. We're actually looking at the validation. One thing to note is that the fractal dimension model on average tends to have lower variance, and it actually reaches a lower loss quicker. In some other, right, so we can sort of see that sort of here, the model could have been trained a little more before it reaches a steady state. One thing we note is that the difference kind of disappeared when we're looking at the Facebook. Again, that could just be the fact that the Facebook model in particular has a very different type of node topology, and the fractal dimension model maybe doesn't have the level of performance that we'd find is statistically significant, such that it makes a difference over the vanilla model. So that's something to consider. Additionally, this sort of second column here. So the first one was the loss. The second one is now that accuracy. One thing to note again is the fractal dimension model accuracy. We still see a little bit of uncertainty here. What's worth noting that these are 95% confidence intervals for those 18 iterations ran. We still see variance, but we still see the model kind of approach that 1 accuracy corresponding to 100%. Again, less so for the Facebook. And secondly, the F1 score, which follows from the macro accuracy, is kind of telling us the same thing. It's just kind of accounting for those true negative false positives. We see variation, but ultimately one thing we found that was consistent was that lower variance. So I think I kind of summarized this here, that we looked at those 3 benchmark data sets, and the graph structure, at least what we found heavily influences the performance of the model in terms of node and feature expression. Node being number of nodes and how they're connected, feature being, okay, so once all the information about those nodes are encoded, whether it be bag of words or in that last one, the Facebook, it was corresponding to, I kind of already forgot it was. So for the Facebook one, the encoded information was 128 node features, page owners. So it's not very clear exactly how these features are extracted, but there is some form of feature extraction step. I can't remember. Owners created to summarize the purpose of the site. So whether it was the use of words or perhaps it was flags, I didn't quite mention that there, but that's a publicly used data set. So worth checking that out. Yes, so we're looking at that. Ultimately, it comes down to nodes. So that's the colors and how they're connected. and feature expression is these stacked feature vectors there. Yes, so the next thing we looked at was we're incorporating this complexity measure. And remember, we're computing the complexity of the embedding space, and then we're multiplying it by a weight and feeding that weight as a the scalar product with the complexity measure back into the model. So these typical models are considered black boxes because you kind of look into the model and it can't really tell you anything about the weight in particular, or you can sort of see as the emergent behavior. But one thing we can draw information from is what the weight itself is doing over time and the gradient of the weight. So we have these two plots here. One's called a first layer and one's called a second layer. You can imagine the first layer is right after the input feature vector. We computed the complexity of the embedding dimension, and then we project it. And in the second layer, we're computing the complexity and feeding it back in. So it's just the first layer, the second layer, and we also tested the third layer as well. So the question is, what are we doing with regards to the weight and the gradient of the weight, which is partial L over partial weight? So at this first plot, one thing that we want to take a look at is the weight is the red and the gradient is the blue. So what are we looking for when it comes to a model that ideally is learning? Well, the weight fluctuates as the model as a whole learns, and the weight should converge. Additionally, the gradient is how much that weight is changing. So ideally, you want it to change a lot as the model is learning and it's being perturbed, and then we have dropout added to the neural network. So there's some bit of a stochastic push in the model to sort of find better global minima. So the weight actually, what we see in this red plot is it does seem to converge to some sort of value here, 0.745, and the gradient does fluctuate a lot, but then approaches something closer to zero. Again, we don't want it to necessarily be zero, but it's converging with the rest of the model. So that's a good sign. Take an example of a model that maybe particularly doesn't work too well, or does work well, but the model's telling us something different, is that this weight starts out at a certain height here, and it goes down and down, and then approaches, and then it goes to 0.54. Okay, so the red is on the, Okay, so the weight approaches a certain value and the gradient approaches zero. Same thing with this model where there's this large fluctuation, and then it seemed to approach a zero towards the end. Same thing with the weight. It found its spot at 0.54. So as the model converges, the gradient approaches zero and the weight approaches a steady state. That's what we want. Again, the whole model is converging, so we want all the components to converge as well. The model can learn how much it wants to show with the complexity measure. Ultimately, this is what we're trying to do. This weight is modulated by the model, and if it's found to be driven to 0.54, well, that's great. It's saying it's paying attention to it, 0.54 of whatever that scalar value is. So that's good, and then the gradient approaches zero. So we know the model is learning. There's quite a bit of extra testing done in the full paper. I don't think this is something that I can fully flesh out in this presentation, but I'll leave the link to the description for the previous paper where I did look at all the different types of event types and the F1 macro and losses for those. So pretty much what I've done previously was looked at the registry events. What happened to my pointer? Looked at the registry file system and thread activity for each one, and then looked at which feature set corresponds to the best model performance. So that was something that's done in the previous work. So the purpose of this presentation, I went straight into some of the more novel work, which is the creation of different model architectures to create and aid in the prediction based on these things. So what do I mean by that? Everything that we've talked about thus far, besides the benchmark data sets, which are testing on, benchmark data, right? For the purposes of malware detection, we're just looking at registry events. All the work that's been done thus far is looking at the registry APIs and creating a GNN, training a GNN, and coming out with a prediction, and then using that prediction to determine benign versus malicious, right? So all that's been done in previous work. So one of the things that was naturally done later is we can vary input space complexity, or interfeature space complexity, and runtime complexity. Those are the three things that vary based on the model. So there's a few different things. Actually, I didn't explain this very well, but let's just start with the one up here. So one of the things that we did was we considered each model separately, and we looked at the macro accuracy F1 score and thus far, and then we took those predictions, and rather than passing it through that final linear layer for prediction, we just took the final embedding layers of each different type of the model trained separately, concatenated them, so concatenated those embedding vectors, embedding spaces, normalized them just because they tend to come out to different scales, then attached the linear and predictions and determine the loss and prediction at the end. The only thing that we're doing differently is we're just combining the predictive models of 3 different models trained. And then this next thing at this middle here is a little different. In this course, this shows kind of an example of a heterogeneous GNNs. This is different than the top in that in the top example, 3 different optimizers are trained separately for these models, and then all those embeddings are concatenated. In a heteroGNN, we actually have the same model architecture. There is a little bit of duplication of the model layers, but ultimately we kind of have to create the same node framework, and then certain nodes pass on information for only certain event types, because not all nodes, for example, with other nodes, had file system activity, right? So pretty much instead of training, I mean, ultimately this difference is instead of training 3 models separately, we're training the same model at once, and all we're doing is considering which edge types actually exist between the nodes. Still one final linear layer, still the same prediction. How does this change? We have different event types corresponding to different colors, and unique weight matrices to make the predictions on a single graph. That's the other thing, is that with this, each of these have different weight matrices. In this one, the weight matrices are also duplicated. So it's also paying attention to how important registry, file system, and thread are. What happens if we look at all this? Okay, so it's worth mentioning that this embedding concatenation is this one up here. This heteroGNN corresponds to this model down here. This feature concatenation, again, this is from the previous paper, but that's just saying, rather than taking the registry, file system, and thread, and all the different APIs and train 3 separate models, let's just take all the APIs of all 3 and concatenate them in the big feature vector of all the file systems, all 3 of these just combined in a feature one, and then train a single model, right? So it's actually not discerning the difference between registry, file system. There's only one weight matrix, right? So you can kind of see the differences. So feature concatenation uses a single weight matrix, and just considers all the APIs the same, pretty much. Embedding concatenation trains all 3 on separate models and then concatenates them. Heterogeneous GNN only trains one model, but also uses multiple weight matrices to learn. So what happens when we carry this out? Well, there's one thing to mention is that the space complexity is different. There's a lot of redundancy and duplication of the optimizers, which are kind of stateful in the model. In that feature concatenation, we're actually only training one model, so it's actually better use of space complexity. Embedding concatenation is the worst because we're duplicating everything. You can kind of look at this T and this E here that are multiplying throughout. So this T and E really adds to the space complexity as it's multiplied throughout. Heterogeneous is the best use. So what do we see here? We see an accuracy and F1 score where both are higher or better for the vanilla and mass radius, which is one of the complexity layer. Everything is compared to the vanilla layer to one of the complexity layers. One thing that we find is that very poor F1 score and accuracy, as noted in previous work, for this feature concatenation model. Ultimately, it's just looking at all of these APIs, added together, and the model just learning them. It's not discerning them differently. So the model also maybe can't pay close attention, and it's making it difficult for it to learn. So poor accuracy, F1 score throughout. The better results when we started using these 2 models, which make better use of learning the differences in the event types. Only difference is space complexity. Heterogeneous GNN does have a lower space complexity, so it's worth stressing that the higher performance and the better use of space complexity is something we want to look at. So what is the complexity layer in effect doing? Well, it's improving model performance through a quicker conversion to the solution space. And what is it doing ultimately? It's a very high order feature extractor. So it's producing a scalar from these embedding spaces. So it's taking this information and extracting it in a very dense representation, feeding it through. So in effect, that's what it's doing. It's a high order feature extractor. One of the things that's maybe one of the more novel aspects from this, and is going to be one of the main points of discussion for the paper that comes of this work, is that once the model is trained, you can imagine we have these highly scored subgraphs and features coming through models prediction. So what does this mean? This means that now we have a trained model and we feed it a new training example it's never seen. And then we can see that certain nodes are of interest. So we see that after the fact. So we look at all the nodes and we, again, have a training example we've never seen. And it says these are benign, these are malicious. We look at the ones that are flagged as malicious and we extract that subgraph. And then we also look at the features that were scored very highly. And we say these are features that are very, that scored very highly. And the way that we do that, okay, I don't quite mention it here, but we used, oh, I did mention here, is that we use G and index player. So we extract that subgraph, we look at the features, we say which features are demonstrating that the model is showing, is indicative of malicious behavior. So we can extract that information. So what do we see? Well, we looked at each of the 3 event types because we did train models for each event type. And then we actually looked at which features, remember these are n-grams, so these are assortment of 1, 2, and 3 different APIs in sequence. And we looked at which one corresponded to malicious behavior. And then you can actually see that in this particular feature vector corresponding to this column, this is associated with the open process virtual alloc and write process memory APIs as a sequence. Again, that's an n-gram of 3. And then one thing to note is that you see these kind of features come up and you can visually see them when you encode them back into their kind of text representation. And then you can see that they actually correspond to MITRE techniques. So there's a little bit of guess and checking and expert advice analysis when it comes to, okay, what API sequence am I seeing? What MITRE technique does it correspond to? Are there some that show up that don't quite correspond to a MITRE technique? And it's just because I didn't visually see it. But ultimately, one thing we found was some of those highly scored API sequences actually correspond to MITRE techniques that are well known in the industry, in the scientific community, to correspond to DIL injection, process injection, registry modifications. Obviously, registry modifications are using the same sorts of API keys, right? And then there's certain MITRE IDs that actually correspond to these. So what are we doing here? We're creating a model that can identify malware and also benignware. So we can actually look at the features that benignware is using and actually note that as a low scoring API sequence. But what it's actually doing is we're extracting these API sequences because the model has learned things. We're extracting them out, and then we can actually take the ones that are flagged as a strong predictor of malicious behavior and extract it out and use that in any sort of maybe Yarrow rule or any sort of other signature base. So we can actually create, through this kind of unsupervised way, we can extract these sequences, even though it's not unsupervised in the training, but we can extract these sequences and use those for signatures as well. But they were learned dynamically. We extracted dynamic behavior and extracted them. Okay, so this pretty much summarizes the contributions of this work. Previous work tested the theoretical foundations of this work one component at a time, starting with the Sandy toolbox, where we looked at the snapshot and execution of malware. Secondly, when this next work here, where we kind of tested the idea of computing the complexity of those embedding layers, but not on a GNN of just a simple multi-layer perceptron. This later work where we actually looked at a graph framework. And this is where we used the process and parent process identifier for the first time and used it to determine maliciousness without the complexity layer. And this work to be completed and hopefully published by the end of the year is just all these ensemble methods and sort of the work that we did to create the theoretical foundations for that. So complexity serves as a very high useful order feature extractor, and we can do this to learn the topology of the embedding space as the model is trained. As that embedding space turns out random, as the weights are initialized randomly, as the model kind of learns and separates those training examples, the complexity layer is there. It's capturing that and feeding it back into the model. Those application, one way to note, is it's not specific to malware detection, but as an accessory for any machine learning application. So in this work here, this was tested on multi-layer perceptron, but there's nothing that says for any other model you can't use it as a higher order feature extractor, a form of compression. That's in effect what the complexity model is doing. So with that, thank you for your time. As always, questions can be put in the comment sections below. I'll get back to you. In the next set of presentations, we're going to cover the appendices items for this work. and then we'll do a bit of a code deep dive. And thanks for watching.